So welcome. Yes, so in certain sense, this is a continuation of what you just heard, because we are speaking about mixed integer semi-definite programs. They are a special case of convex min-RP. They are nonlinear, and so they are also the generalization of mixed integer programs. Sorry, linear programs. So this is what I plan to tell you. We do a little bit of warm-up, some preliminaries. Then I'll show you some applications, and then we'll speak about solution methods, because that's written in the title of the talk. Then SCIP-SDP is one solver. I'll tell you a bit about it. And then I'll go through some techniques that we use, and we'll see how much time we have for this. And then I'll end with conclusions and, of course, questions from you. Actually, if you have questions, just ask in between if you like. Okay, so as a warm-up, I've collected some facts from linear algebra. Maybe you remember, maybe not. So we start with a symmetric matrix M, n by n, and actually all matrices in this talk will be symmetric. Maybe I forget about this, but they will all be symmetric. And then this matrix M is positive semi-definite, which I'll abbreviate with PSD. And I'll denote it by this M curly greater or equal 0 if the product of any vector x from the left and right on M is always non-negative. Okay, so this should be somehow familiar to you, I hope at least. And this is equivalent that M has all non-negative eigenvalues. So the matrix is symmetric, so all eigenvalues are real. And if they are all non-negative, then it's positive semi-definite. And you can also characterize it by such a factorization into S transpose S with some matrix S, R times N. R is the rank of M, and if you can write it like that, then it's also positive semi-definite. And then the set of all such matrices, so symmetric, positive semi-definite definite matrices M, this is a closed convex cone, and this is why we are in the convex realm. And then we'll need a bit of notation. So for two matrices A and B, we'll write their inner product. So where we sum up all the pairwise products of all entries by this angle brackets AB. So this is the inner product of this space. And then we'll need one fact. So if we have two positive semi-definite matrices, then their inner product is always greater or equal 0. It's not hard to see. We'll just need it at one place, I think. And then at one place, I'll also need positive definite matrices, which I denote by this curly greater than 0. And there, this product of x on the left and right should be positive as long as x is non-zero. So this also should be familiar. And then I use this bracket around M, where M is a natural number, to denote the set 1 up to M. Okay, so this is the warm-up. Any questions on this so far? Okay, maybe later. Okay, now we'll move slowly from linear programming, which I assume you are familiar with, to semi-definite programming, and then we'll add integer variables to reach the topic of this talk. Okay, so I've written down a linear program, primal and dual, in a bit unfamiliar form maybe to you. So on the left, we have the primal, and we have these vectors A0 up to AM. The objective is to maximize a linear objective as usual in linear optimization. And then we have equality constraints, M equality constraints, which I've splitten up. So you are probably used to the matrix form. If you write these vectors A1 up to AM in the matrix as rows, then this is the same as I've written here. And then X should be non-negative. So the left, the primal, is just the standard form of linear optimization, linear programming. And the dual is on the right. So we minimize the right-hand side of the primal times the dual variables, and then we have inequality constraints. So we sum up these vectors a1 up to am times yk, and then we subtract the right-hand side, and this should be greater or equal to 0. Okay, so again, if you write the vectors in a matrix, then this is A transpose Y minus A naught greater or equal to 0. Okay, now we want to generalize this to matrices. So we just turn the vectors into matrices, and we turn lowercase letters into uppercase letters. Okay, so we have A naught up to am. These are now n by n symmetric matrices, and B stays the same. And then I'll use everywhere where I use this transpose. I now use the inner product, and I capitalize the all letters. And then I get the primal and dual form of semi-definite programs or semi-definite optimization problems. On the left, again, the primal. So we are maximizing. I've written supremum. I'll come back to that later. Why? So we are maximizing a linear objective. So this inner product is a linear objective on the matrix variable X. And then we have equality constraints. So the inner product of all these matrices, A1 up to AM times this X should be BK. And then X should not be greater or equal to 0, but positive semi-definite. Okay, and then the dual on the right-hand side looks similar to the dual in the linear programming case. So we are minimizing, again, B transpose times Y, so that actually stays the same. And then the constraints are, we add up the linear combination. So we take a linear combination of these matrices A1 up to AM with this vector Y, and then we subtract A naught, and this should not be greater or equal to 0, but positive semi-definite. Okay, and then Y is again an M vector. So these are the primal and dual pairs of semi-definite programming, and so I abbreviate this with SDP as usual in the literature. And now if you look closely, then this is a generalization of the linear programming case. Namely, if all of the matrices are diagonal, then you get exactly the same thing as above. Okay, so it's a direct generalization, but it can do more. We are in the matrix space, and we have positive semi-definite constraints, and that's a nonlinear constraint. Any questions on these pairs? So it's very intuitive, I think. I have not argued why this is correct, but I hope it's intuitive. Yes. 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 I'm not quite sure whether I understood the question, but you're asking why I'm using supremum and infimum instead of maximum and minimum. Yes, so the problem is that with SDPs, the objective value, the optimal value might not be attained. That's different from linear programming. Okay, I'll come back to that on the next slide. So there are certain conditions which guarantee that it's attained, but it's not always attained. Okay. Any more questions? Okay. So let's look at the duality relation between them. So I've already introduced primal and dual. So the question is, what is their relation? I've copied them on the top. These are the same primal and dual SDPs as you've seen on the previous slide. And now the question is, of course, do we have a same relation as for linear programming? So namely that the values of these problems are equal as long as they are bounded. or both feasible. And so weak duality, that means that the primal always gives a lower bound on the dual. That is true as well for SDPs, and that's very easy to see. So imagine both problems are feasible. So we have such a matrix X hat for the primal, and we have a feasible solution Y hat for the dual. And then what we do, so because Y hat is feasible, then this linear combination that we see, if I point to the screen, do people see it online or not? Not so much, okay. But I cannot point, can I use, here. Okay, so this matrix here is positive semidefinite, and I've told you that if you multiply it by a positive semidefinite matrix, the inner product is greater or equal 0. Okay. Now we multiply everything out, we get this relation here because this k times x hat is bk because of the constraints of the primal. Okay, so we just plug this in, so we get the sum over bk y hat k, and then we get the inner product of a naught with x still staying there. And then, of course, this sum is nothing else than the inner product of b and y hat. Okay, and because this difference on the right is greater or equal 0, that just means that the value of this feasible solution x hat, so a naught times x hat inner product, is less or equal than b transpose y hat, and this means the value of the primal is less or equal to the dual. Okay, very easy. It's exactly, or almost exactly, the same proof as for linear programming. And now, of course, the question arises, do we also have strong duality? So can we prove that there always exists an x hat and y hat so that the values are equal? Okay. And under certain conditions, that is true, namely if the Slater condition holds. The Slater condition says, so the Slater condition for the primal says that there exists a matrix X, which is positive definite, so not positive semidefinite, but positive definite. This means it lies in the interior of this cone I've talked about. And it should be feasible for P. So this means the primal should have an interior point, feasible point. And for the dual, it means that there exists a y such that this linear combination minus a naught is positive definite. So this matrix should be in the interior of the semi-definite cone. Okay, these are the Slater conditions, and they guarantee that strong duality holds. And then if the Slater condition for the primal holds, then we know that the optimal value for the dual is attained, so that we actually find a y so that this infimum is attained. So B transpose times this y is actually equal to the infimum. And conversely, so if the Slater condition for the dual holds, then the primal value is attained. Okay. Usually, if these conditions do not hold, then this breaks down. Okay, this is in a certain sense problematic for algorithms, as you can imagine. So you cannot simply dualize and say that this is equivalent. So you have to think about when do the Slater conditions hold or not. In practice, there are certain ways to work around this. Okay, and there's also a theory to somehow handle this. This would lead too far for this talk. Good. So what this slide should reveal is that, again, we have this duality relation, but it's a bit more complicated as in the linear case. Okay, this is the takeaway for you, but it won't be too important for the rest of the talk. But nevertheless, any questions on this slide? Yes. Yes. Well, it's a sufficient condition. Okay, so there might be cases where it's not characterizing that this is the case, but for both, if it holds for both, then we are sure that strong duality holds. Yes. Okay. Some comments about solving SDPs. That's very important because that will be the backbone of all the techniques that will follow. So first, theoretically and also practically, SDPs can be solved in polynomial time up to a given accuracy, epsilon, positive epsilon. For instance, by interior point solvers. Again, the world is a bit more complicated here because there might be optimal solutions that are irrational, so they cannot be represented finitely. Okay, this means we cannot expect that there's a finite algorithm to solve it. That's, again, much different to the linear world. If all the matrices and vectors are rational, then we know that there's a rational solution. It's not true here, but anyway, for practice, that's enough. So we can solve it quite efficiently. I'll come back to that, up to an epsilon. And then for these interior point methods to hold theoretically, again, they need this later condition for both the primal and the dual. So if you look at the convergence proofs of these interior point methods, they need both conditions. In practice, we are sometimes lucky or often lucky that they still work if the conditions do not hold, but we cannot be 100% sure. And one difference, again, to the linear world, there is no combinatorial algorithm. So I would call the simplex algorithm a combinatorial algorithm because you can write down an optimal basis and you can check whether this is optimal very easily by linear algebra. So not complicated, but this does not exist for SDPs. And then this is also one complicating factor. And also a difference is restarting is quite complicated. So there are lots of works that try to make interior point methods restartable, so that if you just change a little bit about your problem, that you can resolve it fast. But that's a bit tricky to implement. That's a huge difference to the linear world, where you can hot start, for instance, by the dual simplex algorithm. And that's the backbone of all the linear solvers, so mixed integer linear solvers, okay, that you can resolve very fast. So this will be more complicated here. And then as a consequence, the solution of SDPs is much more time consuming, unfortunately. So there will be roughly a factor of 10 to 100 difference to linear programs. And that means we are somehow also limited in the size. But if you look at the past of linear programming, and you have been introduced to this, I guess, then there's a huge progress, and we can hope for such a progress for the SDP world as well, but it will lag behind the linear case. Okay, so the message of this slide for you is, okay, there exists method to solve SDPs, at least up to a certain accuracy, and we will just use that techniques. And then, yes. Karosh-Kontaka optimality conditions. So these interior point methods actually compute a solution to a certain system, KKT system, and for this to be equivalent to optimality, you need these conditions. It's not important for this talk, but just that you know. Okay, and then we are finally at the topic of this talk, namely mixed integer SDPs. So what I've done here, I've taken the dual form of the SDP, as you can see, and then I added bounds for the y variables, li less or equal yi less or equal ui, and some of the variables should now be integer. Okay, so the set capital I denotes the indices that should be integer. Okay, and the bounds are there because we need them later to branch on them, essentially. So they will encode how we branch. But everything else is the same as before. And now it should be obvious that this is a generalization of mixed integer linear programs, just because SDPs were a generalization of linear programs, and we've added integrality constraints on. Okay, so this is even more complicated than mixed integer linear programming, but of course we can try to borrow techniques from there. Okay, so this is the topic of the talk. And now I'll try to convince you that there are interesting applications. I go through the first application in a bit more detail and then be faster for the remaining ones, but you can slow me down if you are interested in details. Okay, the first application is robust trust topology design. That's a very classical example for SDPs and also for mixed integer SDPs. So what is this about? So you want to design such a trust structure that you can see at the bottom left. So you have certain bars and they are fixed on the left-hand side to a wall, and then a certain force pulls on this truss and it should not break. Okay, so it should withstand the force that is indicated by this arrow pointing down. And so notation, so we have n nodes, these are these little circles, and we have nf free nodes. These are the ones that can move, so they are not attached to the wall. And then we have m possible bars. These are bars that you can choose from, okay? So that's the design task. So you have m edges or bars, and you should choose among them, so that this force F, which lives then in the dimension of your space, D, 2 or 3 usually. I've not seen any trust topology design in 4 dimensions so far, times the number of free nodes, because only on the free nodes this force is actually in place. So the fixed ones, the force does not matter. Okay, and now the design task is we should choose cross-sectional areas of each bar. Okay, and we want to do it in such a way that the volume, the total volume, in a sense, this is the cost of the truss, should be small, but the truss should be stable. So it should withstand the force F. And how is this measured? So stability, in a sense, is measured by the so-called compliance, which is the inner product of this force vector F times displacement vector U. So displacement vector U is, if you apply the force, then this truss will slightly bend, and this change of the positions is measured by U. And the more it bends, the less stable it is. Okay, so, and this inner product measures the potential energy that is stored in the truss, and the larger it is, the less stable. And then if you increase the force on and on, then sooner or later it will break. But we don't want this to be happen, of course. And then the cross-sectional areas can, of course, be chosen to be 0. So then this means that certain bars will not be there. Okay. And so you get from the ground structure the possible all possible bars to a certain choice with the cross-sectional areas on the right. So this is the game here. And now we are making it more complicated. Namely, we add uncertainty. Okay, so such trusses usually should not withstand only one force, but if possible, all forces that are imaginable in practice. So if you look at certain bridges in Dresden, then they should withstand all forces, okay? Also water forces and so on. And so this is modeled by this uncertainty set here. So we now not have a single force, but a set of forces, and they here are modeled as ellipsoids given by this matrix Q, and you bound the Euclidean norm of this vector G that produces F. Okay, so, and what we want to do now, we want to design the truss such that it can withstand every force in this set. So every force in this ellipsoid. Also, if you push it up, it should not break. And then, of course, what we can also do, we can add integrality constraints, namely we can choose the cross-sectional areas not just arbitrarily, but from a discrete set, namely if you want to buy the trusses in a shop, then you will only get them in certain sizes, and so we want to make that discrete. Okay, and then we end up with a formulation like this. So this with uncertainty, this comes from Bental and Nemirovsky, and then Sonja Maas added integrality constraints. And so how does it work? So let's go bottom up. So we have binary variables here, x, a, e, and it says which of the cross-sectional areas that we can choose from are selected for a certain bar e. Okay? Then the first inequality constraint says we can choose at most one for each bar. Makes sense, yeah? And you can also choose none. So this means the bar is not existent. And then we have the semi-definite constraints, constraint which says that the compliance is bounded by C max. C max is a bound on the compliance, on the potential energy. And Q is this matrix that describes this uncertainty set. And then you have this matrix A of X. So it depends on the cross-sectional areas that we choose. And is given as below this. It's the stiffness matrix if you know what this is. If you don't know, just forget about it. And then the objective is we sum up over all bars, then the length of each bar times the cross-sectional area that we choose, and this is just the volume. So this, we minimize the total volume. Okay, so this is one mixed integer semi-definite program. So you can rewrite it very easily in the form that you've seen in the definition. One application. Now let's quickly look at two others very quickly. So the first is cardinality constraint least squares. So it's a regression problem where we want to minimize this regression term, so the Euclidean norm difference of ax minus a vector b. B is measurements, x are your design variables, and we want to regularize them. So we add this square Euclidean norm of x, and we have a cardinality constraints. At most, k of the components of x should be non-zero. Okay, that's a certain, yeah, it's a well-known model in machine learning. And you can write it, and that was shown in this paper that is given here as again, a mixed integer SDP that looks like this. The details are not so important, but I just wanted to show you that such models or problems can be formulated as mixed integer programs. And then the second very fast example is minimum k partitioning. We are given an undirected graph. We want to partition the nodes into k parts such that the sum of the weights within each parts are minimized. And so in the picture that explains it all, so we have three parts, blue, green, and red, and we want to minimize the weights within the parts, and only the blue part has an edge inside the blue part, and that is counted. And the other ones, they don't have this. Okay, so it seems like a good solution for this partitioning problem. And this has many applications, and you can, again, write it as a mixed integer program like this. Yeah? And you can also add bounds, of course, on the sizes of the partitions if you want that they are not too large or not too small. Okay, again, so this was, there are many more applications. I just wanted to, so the message to you is not the details of the applications, but just that you remember that there are certain applications that can naturally be formulated as mixed integer SDPs, okay? There are often many other models around, but they are quite natural for these problems. Okay. So now we've somehow finished the introductory part, and we'll come to the solution methods. How do we actually solve mixed integer SDPs? Okay. There are three methods, and some of them have been mentioned in the talk earlier by Xenia. So the first is a nonlinear branch and bound methods. It's called SDP-based branch and bound. I'll explain how it works on the next slide. And then there is an LP, linear programming based branch and bound methods, where we use linear inequalities, and I'll also explain how this works. And then there's outer approximation, where you derive mixed integer linear programming relaxations, and you repeatedly solve those. I will not speak about this. There's only one implementation, but I will speak about the first two. And at the bottom, you see that there are certain codes that can deal with these three methods, or they implement these three methods. Okay, how does the first work? Very easy. You do it as for linear problems. You relax integrality, you forget about it. Then in our case, we get an SDP, semi-definite program. Okay. And how do we get a branch and bound tree? Well, we branch on the integer y variables, like in the linear case. Okay, then you build up a tree, and in each node we have an SDP, and we have to solve that. The relaxations can then be solved, for instance, by interior point methods, as I mentioned earlier, but the literature, there are also many other methods. They have been tuned towards this approach. And then, of course, somehow you should ensure that they are successful, so that the conditions, for instance, the Slater conditions, are somehow satisfied, if you can control this. So this side somehow has implications for the modeling of your problems as well. And then remember that we don't have a warm start, so we have to, in each node, we have to solve essentially the problem from scratch. That's a downside of this approach, but on the other side, these relaxations are usually very strong, so you will need less nodes in total to derive similar bounds as in the linear case. Okay, so this is really quite natural. You just replace linear relaxations by SDP relaxations. That's it. Okay. Now the second, the LP-based approach. How can we derive a linear relaxation for this non-linear object of positive semi-definite matrices? So we can, of course, use the techniques that Xenia introduced. Namely, we can rewrite the whole problem as a min-LP, convex min-LP, and then apply gradient cuts. So how would this work? So imagine we want a matrix Z to be positive semi-definite. Then we can define such a function G of Z, which is the negative of the smallest eigenvalue of Z. And if I require this to be less or equal 0, this means all eigenvalues should actually be non-negative. So the matrix should be positive semi-definite. Okay, so then you can rewrite this SDP constraint as a nonlinear inequality and apply everything Xenia has told you. And usually this will add gradient cuts. They look like here. So at a certain point, Z bar, you add inequalities like that. They are now linear in Z, in the Z variables, because the gradient is taken at the fixed point Z bar. And then you get really, really many of these linear inequalities, and you add them. The problem with this approach is that this function G is not differentiable. So you would have to take more care. And in practice, it turned out that the following approach is easier and faster, and it works as follows. So we take the characterization that Z is positive semi-definite by the very definition if U transpose Z times U is greater or equal 0 for all vectors U. So what do? Imagine the matrix that we want to be positive semi-definite. This is this matrix here, which I call Z here. Yeah, for some vector y star that comes from the relaxation. And imagine it's not positive semi-definite. We want to enforce that. Then we compute an eigenvector V to the smallest eigenvalue. So because the matrix is not positive semi-definite, this eigenvalue must be negative, right? It must show that the matrix is not positive semidefinite. And then we just add this inequality here. Namely, we take this vector v, multiply it by z from the left and right, and force this to be greater or equal 0. Okay, and if you now plug in the definition of z and multiply everything out, you see, if you look at it for a second, that this is a linear inequality in y, because v is a fixed vector. Yeah, and then you get a linear inequality in y, and you just add those. And then you repeat. Okay, you solve a linear relaxation in LP, you get y, you check whether the matrix C is positive semidefinite. If it's not, you add such a cut and repeat. Okay, and you can imagine that usually or often, this might require a lot of cuts to approximate this nonlinearity. Okay, let's discuss this just for a second because there's an important difference. So maybe you have heard of mixed integer second order cone problems where it's very similar to SDPs, but the constraints require that a certain second order cone condition holds. And for their theory is much nicer because you can show that you can approximate the corresponding sets by linear inequalities very well or by extended formulations. However, and this is the message for you, the bottom theorem, for SDPs, this is unfortunately in general not the case. So the theorem says that there are certain semi-definite programs of dimension n times n, so this matrix C is n times n, where every polyhedral approximation, so whenever you take linear inequalities to approximate this semi-definite constraint, will need exponentially many inequalities. Okay, in a sense, this is bad message for us because we cannot expect in every case that this linear approximation will work well. So it might take very long and add many inequalities. Okay, in practice, this is not always the case, as we will see soon. Okay, let's just before I show you computations, speak about solving the problems and about SCIP-SDP. So SCIP-SDP is one solver to solve mixed integer SDPs. It's based on SCIP. You've heard the name. And it supports both SDP-based branch and bound and this linear approximation, LP-based approach, which I just discussed. And so it was developed in a series of dissertations. It's free. You have the links here. You can download it. You can check. There's even a MATLAB interface. It needs interior point solvers to solve the SDPs, or any solver actually to solve the SDPs. Currently, it interfaces to Mosaic, DSDP, and SDPA. And you can read in several file formats. Also, there's a parallelized version, and it supports rank 1 constraints, which are even harder to solve, but just as a side comment. So, okay, this is one solver. And of course, if you set up a solver, there are many components that you have to take care of. You don't have to read everything that is written here. This slide is a reminder for me to tell you that if you build up a solver, then there are many components that you have to implement to make it effective. Like you have to take care of the constraints. You have to devise primal heuristics. You have to do pre-solving. You have to take care of the relaxations. You have to interface to the solvers. And all this is done in SCIP-SDP. Okay, and I could talk for hours to tell you about all of that, but I will just pick out some of the techniques later. Now, for the computations, I've written down how they are taken. With SCIP-SDP, they are not important now, but if you want to look it up later. So here's an interesting experiment comparing the SDP-based branch and bound and the LP-based branch. Okay. So I've taken SCIP-SDP on 185 instances, and you can see the results. At the top, it's on all instances, and the bottom block is only on the ones where both approaches solve the instance to optimality. Okay, you can see that the SDP-based branch and bound solves many more instances than the LP-based branch and bound, namely 167 compared to 109. If you look at the bottom block, you see on the instances that both solved, then the LP-based branch and bound is much faster. So by about 32%. So what does this mean? This means you cannot always expect that the linear approach works fast, but if it works, then it's fast. Okay. And then, so actually in SCIP-SDP, you can solve both in parallel and stop whenever one is done. Yeah? So you can take advantage of this if you like. Good. So this somehow closes the block on, there's also in comparison to other solvers. I'll skip that. It's just, I mentioned the other solvers, and SCIP-SDP is faster than them. Okay, so this concludes the block on solving mixed integer SDPs. Any questions on this block? Anything unclear? Yeah. So this trust topology is okay. Cardinality constraints okay. So the min k partitioning, it's not so good. We can see here, we can actually see, so this TTD is this trust topology, CLS is cardinality least squares, MKP is the minimum K partitioning. And what do we see? The top two rows, it's better for the CLS, it's not so good for the trust topology, and it's really bad for the partitioning. Yeah. Any other questions? Yes. You mean whether I can somehow use if they know that? I don't think so. No, it would be an interior so that it lies in the interior. I don't think it has advantages. So in the relaxations, you will usually get a solution that is on the boundary. So it's actually not positive definite. So, and I'm not aware of any approach that somehow uses this. Okay, so let me look at the time. I have 5 minutes. Okay, then I was much slower than I expected. Okay, then you choose what I will tell you. So there are 3 topics to choose from. So I can talk about presolving, and I can talk about conflict analysis, and I can talk about symmetry. Only one. I have only the time for one. So, no, we will vote, of course. So, okay, who wants to hear about presolving? Okay, who wants to hear about conflict analysis? This is a bit more, I think. And symmetry? Oh, that's difficult to say. So I think conflict analysis was slightly more. So let's jump to conflict analysis. Timo, have you told them about conflict analysis? Fantastic. Fantastic, this fits. Okay. Okay, conflict analysis. So what is the idea of conflict analysis? The original idea was to somehow learn if you have a branch and bound tree from infeasible nodes. Okay, so in the original branch and bound algorithm, infeasibility has just been used to cut off the node, but that's it. You're not learning anything from it. And the idea was, can we somehow make use of the information that I know that the node is infeasible? Okay. And the original idea comes from SAT solving and was transferred to mixed integer programs by Tobias Achterberg. And in the meantime, there have been several rounds of generalizations, for instance, by Timo and Jakob Witzig, where it's about learning inequalities cuts from these infeasibility arguments. So this is called dual ray or solution analysis. So how does it work? So imagine we have this mixed integer SDP. It is actually exactly the same before, except that I added some linear inequalities dy greater or equal d. They are not important, but we can do it, so why not? Okay, and imagine that we have a positive semidefinite matrix X hat and a non-negative vector Z hat greater or equal 0, obviously. And now we can aggregate the constraints of this program. So first, as you've seen in the proof of the weak duality, we can take the inner product of X hat with this matrix A, Y. It's defined up there. The linear combination of the matrices AK and minus A naught. Okay. So as I told you, if Y is feasible, then this AY must be positive semidefinite. X hat is positive semidefinite, so their inner product is greater or equal 0. Now, then we can also aggregate the linear inequalities by multiplying with the C hat from the left. Okay, so if X or if Y is feasible, then this will obviously again be feasible if I just add them up or weigh them and add them up. Now, of course, what I've just done is this is an inequality that is redundant, right? I've just derived it from the constraints directly. So if the original constraints are satisfied, then this inequality is satisfied as well. However, in the algorithm, you can do bound tightening. So if certain variables are fixed, you may fix other variables, and you can make use of integrality. Okay? So this is why the inequalities might be valuable. So how do you get them? There are essentially two ways. It looks a bit complicated, but it's actually quite easy. So either the solution of your node is infeasible, then the dual can often produce a ray or a feasible solution. At the top, this is the dual if you also have these linear inequalities and bounds on the variables, and at the bottom, this is the program if you're unbounded. Okay, and whenever you have a feasible solution for either of them, you can derive such a cut. And the lemma at the bottom says, if you take, for instance, the primal ray and you derive the cut from the previous slide. So you take the X hat and the Z hat from one of those two and derive the cut here, then this will be infeasible if you if you have such a primal ray. This means your node is infeasible. So this is just a confirmation that the inequality that we derived is actually able to certify that the node is infeasible. Okay, and the hope now is that this inequality here is valuable in other nodes as well. So why not? If it shows that a certain node is infeasible, maybe it also shows that another node is infeasible. And in fact, that's what happens, and this is why you can learn from infeasible nodes. Okay, here, if you implement this in SCIP-SDP, or I actually did it, then you will see, so the default is no conflict analysis. Conflicts is with conflict analysis. And again, at the top, all instances, at the bottom, all that can be solved by both. And you see that we get a speed up of about 8%. And the surprising thing is that we actually produce one such inequality, more than one inequality per node. That's because we also run primal heuristics, and the primal heuristics, they will also produce such cuts. And one further thing, we can derive the same cuts also by feasible nodes. It's not only learning from infeasible nodes, we can also learn from feasible nodes by doing just the same thing. You just aggregate, write down an inequality, store it, and apply it whenever it helps. Okay, that was conflict analysis in a 5-minute rundown. Okay, let's jump over symmetry and come to the conclusions and outlook. So what should you take away from this talk? So first, I hope that you have understood what mixed integer SDPs are, why they might be useful, also the possible complications that you have to deal with, but also that it's possible to generalize many of the methods that you've seen for linear programs. And there are many techniques that help to improve performance. Conflict analysis, just one of them. And the bottleneck of all approaches is solving the SDPs. So most of the time is spent in solving the SDPs. However, you also get something from it. You get strong bounds, and this reduces the number of nodes. And the future, or the hope for the future, would be that we see a similar development as for linear mixed integer programs. So that means that we see a similar speed up in solution time as for the linear case. Yeah, thanks for your attention.